coordinates, and we converted one direction. I'm not sure if we converted the other direction.
We did.
We did? Both ways? Okay. So we are going to just start graphing. Okay. We're just going to do point plotting. So for example, we are going to graph r equals 4 sine theta. Okay. You know what? Actually, I kind of make my t-chart the other way because I put my angles here and my r's there. Okay. So this right here is 30 degrees. I mean, unless you want to keep using your pi button in your calculator, we're just going to do degrees, and then we're just going to punch it up and get our decimal approximations. So we got 45, we got 60. If we want, we can do 75. These are increments of 15 here. Okay, 90. All right, so let's just do 0, 30, 45, 60, 90, 120. All right, does everybody have their listening ears on? Because I'm going to give you an angle measure and you're going to have to punch it up. All right. Emily, 0. So you're going to plug in 0, take the sine of 0, multiply by 4. Sawyer, 30. Lauren, 45. Britt, you're going to do 60. Tiago, you got to use your calculator. You're going to do 90. Sarah, 120. Lexi, 135. Jonah, punch up 150. Justin, no, not Justin. What am I talking? William, no. Patrick, 180. And I'll do 210. And whoever can do 225, because they had an easy one, because it was like 0 or 1, you could do that. Make sure you're in degree mode. Oh, dang it. Oh. All right, so when you get your answer,
90 is 4.
Huh?
4 is
4.
90.
90 is 4.
60 is 2 root 3.
2 point what?
2 root 3.
Put your calculator in decimal mode.
3.46.
3.4?
Yep.
3.46?
Yep.
Okay, here we are for the one time in the class. I am not going to make you write this in radical form because graphing 2 root 3 is,
225 is 2.8.
What are you doing? Oh, 225?
Yeah.
What'd you get?
Negative 2.8.
2.8.
135 is 2.8.
2.8. Who got 45?
You want decimal?
Yeah.
I got 2.8.
Okay. Emily, did you get yours?
0.
0. Sawyer?
2.
2. Who had 120?
Me, and it's the exact same thing as 60.
3.5. 150?
2.
Huh?
2.
2. 180? Easy one.
3.5.
What happened to 180? 0. All right, let's plot. What you want to do, so here we go. So 0, 0, we're going to plot. I look at my angle first, and then I go out my R length. 1, 2. 45 is 2.8, so 1, 2, 3, so 2.8, just guesstimate. 60 is 3.5, so 60 is this ray, 1, 2, 3.5. What you might want to do is kind of start connecting the dots. This is very much connect the dots rather than getting all your dots and try to, it's going to, due to the nature of the sine and cosine curve, it will flow very nicely. And if you just kind of plot all your dots, this one you probably won't get messed up, but we're going to do a rose curve next. And you might be like, I don't even know where to go. So if you just kind of plot a few and draw, so this was 60, next we're at 90, so straight up 1, 2, 3, 4. Then 120 is 3.5, and 135 is 2.8. 2.8. We can continue to rotate. 135. 150 is 2. 1, 2. 180. What's 180? 0. I'm going out 180 degrees, but I'm going 0, so where am I? Just the origin, okay? And if we connect the dots, 210, -2. What happens when I go 210 with -2? What happens? We go back the other way. So we're actually coming back this way. Okay, look. 225 is the 45-degree angle in the third quadrant, but we're going to shoot backwards since our R is negative. 2.8. And if I continued, I would continue getting these 3 points and create a circle. Okay. Your polar graphs, with the exception of spirals, will overlap upon themselves after a certain length of time. Here it took 180 degrees to create the full graph. If we went and graphed the points from 181 through 360, we're just going to go around it again. Some of your homework problems will be needing 360 degrees to graph. I want you to do T-charts. Okay, I understand that some of your homework problem instructions say to use a graphing utility. We're not going to use the graphing utility. If you want to use a graphing utility to check, most of them are all even or odd anyway, so you can be able to do it. You can absolutely, but I want you to get the T-chart experience. I want you to plot the points. I want you to get the experience of graphing. All right. In addition to graphing, another thing that we are also going to do is convert our polar equation into rectangular format, just like we took polar points and converting them into rectangular format. So, convert R equals 4 sine theta into a, rectangular equation. All right. So polars that R and sin theta is rectangular has what?
X and Y.
X and Y. So we're going to get rid of R's and thetas. We're going to get X's and Y's. So some relationships that can help us is, what do you know about sine theta?
Y over R.
Y over R. Cosine theta is X over R. We've got all of those. Tangent theta is Y over X. Okay. Also, if we go back to the fact that if we're going to sketch, if this is the coordinate X comma Y, so then this is X and this is Y, this makes a right triangle. This is my angle theta. Our R, what do we know about R with respect to X and Y?
It's greater.
It is totally greater, but
It's the sum of the squares.
the sum of the squares. So we also know that R squared is equal to X squared plus Y squared. Sometimes it's helpful to say that R is equal to the square root of X squared plus Y squared. So we've got relationships that you've been dealing with for the last 2 months, possibly. Yes. Okay, so now we're just going to convert. So we've got R equals 4 sine theta. Okay, I'm not bothered by the R just yet. But my first thing that I'm looking at is that sine theta. What can I substitute in place of sine theta with the goal of getting to X's and Y's? Sine sine theta is y over r. So now we've got 4 times y over r. Whoops, that was supposed to be y, but anyway, r. Okay, so I've got y, so that's good, bonus, but I do have r on both sides. And I know you love the fraction on the right-hand side. Okay, so if you're like, I want to just get rid of that fraction on the right-hand side, what might you do?
Distribute.
We could distribute, but what if we just multiply both sides by r? So if I multiply this by r, you know it's over 1. If I multiply this by r, so here I cancel, and we end up getting 4y. And over here I get r squared. And I'm so excited about r squared because I know r squared is x squared plus y squared. And how do you know when you're done? If all you have are numbers, x's and y's. Okay? I'm fine with you leaving it like this. Okay? As a small review, I already kind of mentioned it, but what's the graph over there?
Circle.
A circle. Okay? Does this look like a circle? You're like, I don't know. Is that circle centered at the origin? No, which means we might have, and in a previous math class, honestly, we're going to do this not necessarily with circles, but do you remember completing the square? Shake your head, yes, it's been a while, but I'm kind of familiar. My y's, we can make this y quantity squared by adding a special number here. You guys remember? How do I figure out what this number is? Take the 4, the negative 4, and divide it by 2 and square it. You get lots of practice with this in chapter 6. So we get 4. So I add 4. Am I allowed to just add 4 here? I have to add 4 to the other side. If you take y squared minus 4y plus 4 and you factor it, I'm going to get a y, I'm going to get a y. What multiplies to be 4 and adds to be negative 4? So like 2 and 2, and oh, if they were both negative, it totally would. And then we get this. Now you might look at this and say, ew, but if we just kind of take a little bit of a small break and remember that a more basic circle is one where I'm centered at the origin and I have a radius of 3. Look familiar? Okay, so 1, 2, 3. Okay, that means this has been translated in the y direction, up to, down to.
Down.
Oh, this is where we gotta be careful. We're gonna have to remember this, think about it. We actually go up to, and it has a radius of 2. So if we put our center here, we can kind of see that, yeah, our center shifted up to. We have a radius of 2. In terms of why did it change sign over there, we'll deal with that when we do much more of it at the beginning, you know, in chapter 6, which is the last unit. Okay. For right now, this was a little bit of 2 minutes worth of just kind of fluff. You can leave your answer like this. I think your book actually sets it equal to 0. How much do I care about that? But you are checking your answer in the back of the book, therefore you probably would say, okay, I'm going to make my answer look like theirs, so you said equal to 0. Okay, if you wrote that on a test, I'd be fine. All right, how are we doing? Those problems, so with respect to the way your homework is situated, it kind of tells you what type of graph you're going to get. And all of our converting problems are these down here at the bottom where it says also 41, 43, blah, 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 blah. Okay. All of your graphs, you're just graphing. you're not also converting. I just killed two birds with one stone. Okay, so you're gonna have some convert problems. Those are these problems down at the bottom here. Don't kind of miss those. All right, next we're gonna graph is, let's go a different color. R equals 3 sine, oh, you know what, let's not repeat values. 2 sine 3 theta. Alright, so you are so excited because you're like, I got this. She's just making me do a T-chart. Okay, so you're like, all right, I'm going to start out. 0, the sign is 0, or plug in 0, 3 times 0 is 0, sign of 0 is 0, multiply 0 by 2, you're so excited. You plug in 30, now I'm taking the sign of 90. You just totally bypassed a whole quarter of a rotation, okay, by jumping to our comfort 0, 30, okay? So that is too much of a gap. You just jump from the sine of 0 to the sine of 90 real fast. So with respect to graphs where you have a multiple of theta angle, we are going to want to subdivide our angle measures a lot more. Okay, so let's just go by tens. We're going to have to estimate. So 10, 20, 30, yeah, it should be fine. 40, 50, 60, 70, 80, 90. We'll see how that goes. And this one you're going to definitely for sure want to connect the dots after like 2 or 3 or 4. All right, so same thing. Already did the first one. So Emily, 10, Sawyer, 20, Lauren, 30, Britt, 40, Tiago, 50, Sarah, 60, plug it in, plug and chug. Jonah, 70, Lexi, 80, and I'll do 90. Patrick, you can do 100. And if you don't know what angle you had, just pick one and do it. You'll double check someone. Anybody have their answer? Yeah?
30 is
2. Good, easy one.
1.17.
1.
40.1. 1.7. Sorry.
Well, you're fine. Emily?
10 is 1.
1.
50 is 1.
1. Which one's that?
50.
50 is 1.
20 is 1.7.
80 is -1.7.
100 is negative 1.7.
Sarah, what'd you get?
Absolutely nothing. 0.
0. Oh, on 60?
Yep.
70 is -1.
Wow, look at this. The symmetry. There is symmetry. Your book does talk about symmetry. So we're just plotting points. We're going to graph. Okay. We're probably going to need more, but we'll start with this and see how it goes. So we've got 0, 0. So this right here was 30. So this is 15. So 10 degrees is, 2/3 of the way from 0 to 15. So you're just going to do the best you can at estimating. So 10 degrees, we are at 1. We can consider, and this might be an actually great idea, the largest value that we are ever going to get is when sine is equal to 1, and 1 times 2 is 2. So what we can do is adjust our unit system. So here, let's go, we'll make this 1 and 2. So 10 degrees, I'm at 1. 20 degrees, so I'm a little bit past 15, I'm at 1.7. So 1.7, do the best you can at estimating.
It's farther than that.
Huh?
It's past 1.5.
Oh, dude, right, I forgot. Okay, so 1.5, 1.7, right here. All right, 30, we are at 2. Okay, So we have come from the origin out here, kind of doing that to here. Okay, so now 50 degrees, wait a minute, oh, we're at 30. 40 is 1.7, so 40 degrees. Now we are back at 1.7. Okay, this is the reason why we want to kind of connect our dots as we go. 50, 40, 50 is this kind of unit. We're at 1, and we've got that kind of symmetry going on. And 60, we're back at 0. Okay, they do call them rose curves, but they'd probably be better called daisy curves because we're going to have petals. All right, 60. 70, let's see, 45, this is 60. So 70 is right there, but my R is negative, so that means we're going to go backwards. So if you kind of get flustered with respect to which one of these rays am I supposed to be focusing on, you could say, well, 2 rays this direction is going to put me 2 rays here, so this is comparable to 60, which is what, 240, or yeah. So forget, I'm not going to label it, I'm just going to put a dot, which means I'm closer to the y-axis by a third. Okay, so that's one way you can kind of help yourself. And we're going to go out 1 unit, which 1 unit is 2 circles. So right here. Then at 80, which is, no, wait a minute, 70. 70, oh, I just did. 80, right here.
It's not passed to the left.
Oh, wait a minute, this was supposed to be 70. I got my 5s mixed up. Anyway, so I'm over here. So at 80, we're at negative 1.7, so we're going to shoot backwards. 1, 1.5, 1.7, right here. At 90, we are at negative 2. And at 100, we're going to be at negative 1.7 right here. You probably, so if we do this, we're doing this. Where do you think we're going now?
Down to 1.
Back to the origin. Okay. So the probability is that 100, so 110 would have put us back at negative 1. And 10 more units, 120. 120 times 3 is 360. The sign of 360 is 0. So we're back there. Okay. So now let's just go another unit of 10. So let's go 130, 140, 150, 160, 170, 180. Okay. We can use our calculator. We can say, well, every unit of 10, the pattern is 0, 1, 1.72, and then it goes back down to 0. Then it's negative. We can kind of just think about it or punch it up once and then continue the pattern. 130 times 3 is 390. 390 degrees is in the first quadrant. The sign is positive, so 2 times positive is going to be positive, so this would be positive 1. Did anybody punch it up on their calculator and get positive 1? So these values, since the pattern goes so well, we can do this 1.7. Well, it's not negative. We can double check ourselves. 150 times 3 is 450. 450 is all the way around and then ending up at 90. Sine of 90 is 1, and sure enough, we get 2. Okay. How often do I do this pattern? Not very often, because a lot of times it doesn't necessarily work so great. But let's just finish. Where are we? Oh, we're at 0. So 130. So let's see, this is 135. So 130, and we are at 1.7, no, we're at 1. Right here. At 140, we're at 1.7. So 150, we're at 2. 160, we're at 1.7. This is 175, 15 degrees, right? No, 165. Wait a minute. Oh, 180. Yes, 160. All right, 170, I'm at 1, and then I'm back at 0. Okay, so it is very symmetric. So you might say, am I done? And you might say, I don't know. How could I check to see if that's the complete curve? Someone, you guys punch up 190, you guys punch up 200.
-1 is 190.
Did you get, oh man, look what I just did. Anyway, did you get -1.7 here?
Mm-hmm.
Okay, so, where are we at? 200, so this is 210. So 200 is coming out, you know, that direction, but it is, oh, excuse me, 190. Here we are, 190. No, wait a minute. This is 210. This is 195. 190 is a third of the way there, which means that we're going to go, instead of this direction, we're going to go backwards. And I'm going to go 1 unit. 200 is a third through here. And instead of going this direction, I'm going to go backwards, and I'm going to end up there. Okay, so it does repeat. So it's like the spire graph I was kind of mentioning yesterday. If you keep going around and around, we're just going to keep repeating the same exact thing. Okay, so this graph also repeated by 180, but we definitely needed more smaller unit of angles to be able to get the whole picture. Like I said, the only graphs that are not going to repeat upon themselves are spirals, and I'm going to write those equations so that we can talk about them. You guys can be successful in your homework with them over your wonderful break.
Are we gonna have to go back from graph to?
Oh, are you gonna have to take a graph and write the equation? Oh, that would be so bold.
Boy.
Okay, good.
Yeah, do for
I
bonus
never
question.
thought of doing that.
Let's not do it for a bonus question.
Seeing as we have to get vectors in 20 minutes, let's just focus on less bonus type questions. Okay, what was I just thinking? Oh, the spirals. 6.5. The one thing about the spirals is put your angle in radians, otherwise it's not going to be good.
Should
All
make-
right, so your spiral equations are number 35 and 37. 35, 37, okay, 35 is r equals theta. You're like, what? In that case, if I was doing r equals theta, here's my theta, my r would be 30. Okay, so at 30 degrees, I gotta be out 30 units, okay? So make sure you use radians. Okay, so for example, 90, so now my t-chart could be just the, you know, the nice, whoops, not x. So, oh, what I did. 0, pi over 6, pi over 3, pi over 2, those are the radians that we're used to. I would go our pi units, and then I would just punch up pi divided by 6 on your calculator. It's about 0.5, it's not exactly 0.5, but it is-ish. This is about 1.1, I'm not really sure. This is like 1.57, so it's 1.6. So do that problem, your spiral in radians, and problem number 37, I believe is r equals 2 to the power of theta. Yes, it's super tiny. They here ask you, they do tell you to graph this one, and then they're telling you what kind of domain. So they write this to tell you that you're going to graph this spiral between 0 and 6 pi. And honestly, I take it back, I wouldn't do this. I would do 0, 1 pi, 2 pi, 3 pi, 4 pi. We could do by halves, that probably would be a little bit more helpful. 0, pi over 2, pi, 3 pi over 2, that kind of stuff. Here, they're saying to graph between 0 and 2 pi. Whoops. But we're going to make sure that when we say, so 0 is not totally exciting, 2 to the 0 is 1. If we're going to plug in, say pi over 2, we're going to make sure we do 2 to the power of pi over 2, and when you use your exponent, make sure you put parentheses around that to get your decimal from your calculator. Okay? So make sure on those two problems you graph with respect to radians. The other ones I don't care. You're probably most comfortable with degrees. Honestly, punching it in your calculator is easier in degrees. And let's see. Oh, look what I did.
If you have tape, you can just tape it down.
Why didn't I have your brain when I was preparing for class? Okay. You know what? I think I'm just gonna throw you to the wolves on, well, throw you to the wolves on converting from a polar equation to, converting from polar to rectangular is a little easier. Do I give you one where you have to go the other direction? 71. You know what, you're going to have a question on it whether I do an example like that or not, so I'll throw you to the wolves on converting a rectangular equation into a polar. Or maybe I'll put a little video out. Okay, so what I want to do is I want to get started on vectors. So I'm going to shut this off. Does anybody have any questions on this before we move on to vectors? Okay. Yes. All right. So we are going to backtrack to chapter 4. Okay. One of the reasons why I like doing polar coordinates before vectors kind of relates to these two expressions. We had them on the board yesterday. If we multiply both sides by r, we get r cosine theta is equal to x, and r sine theta is equal to y. And they're going to be a little bit helpful when we're dealing with some pieces, some aspects of vectors. All right. We might actually not get to why would I do that today. No, we will actually. Maybe, I don't know. Okay, so 4.3. Okay, so we have a vector. Okay, that vector is free moving. I can have it there, I can put it here, I can put it here. If I put it on a grid, it can be anywhere in the grid. Okay? We are going to describe, oh man, going to describe vectors based on the pieces we're most comfortable with respect to an XY plane, an XY rectangular coordinate system. So we're going to describe it with respect to how far over does it go and how far up does it go. Okay? So for example, this might be 3 over in the X direction. This might be 2 units up in the Y direction. And there's 2 ways we can write this. We've got angle brackets, 3, 2, which means 3 units horizontally along with X and 2 units vertically along with Y.
So it's like a ratio.
Huh?
It's like a ratio.
Exactly. Okay, it's kind of like slope. Don't write it in slope fraction form, but exactly. Okay, and this vector here, which we could call the book, they use bold variables to indicate vectors. I can't really do bold so well, and so I kind of put a little arrow on top. So if that's vector V, and this is vector W, and vector W goes over 3 units and up 2 units, vector V is equal to vector W. Okay, so the location of the vector doesn't really matter. They are free moving, they could be anywhere. They could be on that wall, they could be this wall. If they're going in the opposite direction, not equal, but they would be opposite. Okay, so in fact, let's do that. Let's flip this one this way. So now it goes 3 units this direction and 2 units down. We can call this -3, -2, and it's almost exactly equal to vectors W and vectors V over and up, but instead of going that way, we go this way, which means it's negative. Just like our polar coordinates, never thought about this, but our positive r's go with the angle and our negative r's go the opposite direction.
So can you have that in any coordinate plane? Or on any, does that
We
make
put
sense?
it anywhere.
Yeah.
Okay, so let's call this vector u. So vector u is equal to this. Now notice, and we know it's the opposite of vector v, and it's the opposite of vector w. So one of the things that's really kind of nice and maybe can be a little comfort for you is that vectors can be very logical computation-wise, okay? If this is vector v, which is what we called it, and I want the opposite of vector v, then each of these components become negative, which we can see that when we created vector u, which is the opposite of vector v, its component is -3, -2. Okay. Suppose we want to double the length. Okay. Hold on to double the length. So there are 2 things that vectors have. They have magnitude and direction. Okay, so if they have the same magnitude and the same direction, then they're equal. Okay, magnitude I didn't really mention. Does anybody know what magnitude is because you already took physics?
It's like a size or like
The
speed or
length.
force. It's length, yeah.
Yeah, the length of the vector. Okay, we haven't actually found the length of these vectors yet because that would just be the hypotenuse. Okay, but based on our conceptual knowledge of triangles that go over 3 and up 2 and over 3 and up 2, then you probably realize that the lengths are actually going to be the same. Okay. Speaking of how do we indicate magnitude, the length or the magnitude of vector v It's not the absolute value. Hold on. I think your textbook does 2 bars. Do they do 2 bars or 1 bar? 2 bars, 2 bars. 3. Yes. No. Yes. So yes, it's not absolute value, it's double bars. Okay. That is indicating the magnitude of the vector. Okay, so if over here we wanted to figure out the magnitude of vector v, you can memorize the formula, and it's really not that hard, but it's not that hard to sketch 3 over and 2 up, draw the vector, and then what are you going to do to figure out the length or magnitude of the vector? 3 squared plus 2 squared equals,
Square root of 3 squared.
technically it's the magnitude of v squared, which looks kind of yucky, but we're going to have 9 plus 4, we're going to get 13, and what are we going to do with 13?
Square root.
Square root. So the magnitude of vector v is the square root of 13.
Would you
Okay.
have to put plus or minus?
No, because the length is always positive. We wouldn't have a minus unless we change the direction on it. Okay? How can I describe the direction of vector v?
Diagonally.
An angle. Now, we have the square root of 13, so we do have all 3 sides, but the square root of 13 is some decimal or calculator. What might be easier to use instead of dealing with the square root of 13? The 2 and the 3, and what trig function might be helpful? Tangent. The tangent of the angle theta that vector v is making with the positive x-axis is 2/3. We punch up the inverse tangent. Who's speedy fast on their calculator?
33.69.
383.7. Okay. So the direction, this is the direction, and the magnitude. All right. Now, what if we consider 2v? Okay. So now, instead of going 1 unit of v, I tack on another unit of v. Okay. If this is the square root of 13 for the magnitude, what would the magnitude of 2v be? Just twice as long, right? So the magnitude of 2v is 2 root 13. If we want to think now, this right here, and I can't remember if I said it, I might have said it before this is component form. So it's going to tell you your horizontal component and your vertical component, just like x comma y. We distinguish it from a point by using angle brackets. Okay, so if I've got angle brackets, it's a vector. Okay. If I wanted to figure out the component form, of 2v, well, if I think about this vector now is twice as long, which makes sense that I'm going to be twice as far over in x and twice as far up in y, and I would get the component form 6, 4. How visual do you have to be? I do trig a lot very visual. I think I don't know if you like it, hopefully you do. But we can just also say 2 times the component form, and it's basically double each portion of component form. So double 3 and I get 6, double 2 and I get 4. Okay. Now, there is another way to express component form. And it has to deal with, or it uses, we're going to define I. Not the imaginary I. We are changing paradigms. We are in a physics, a science, forces, all that kind of stuff. I is a unit vector in the direction of the positive x-axis. Okay, it's an I, italicized I. J is a unit, this is J, so you got your tail going one way, your tail going the other way, you're just going to have to be careful. But it's a unit vector in the positive, in the direction, sorry this is so messy, positive y-axis. Okay, and so that diagram is getting fairly complicated. Vector V was 3 over and 2 up. Well, it's 3 unit vectors of I. Okay, I was supposed to remember to mention a unit vector is mean it has length 1. So if my I unit vector is in the positive x direction, I've got 1, 2, 3. Okay, I got 3 I's. And now I'm going to move up, which means I'm going to do J. Oh, I'm supposed to have 2 of these. J, J. So we can express it as 3I plus 2J. We didn't get a chance to talk a whole lot about adding vectors, but when we add vectors together, we connect them tip to tail. So we just kind of connect them. If you think about, you probably know, well anyway, if you have your airplane going this way and the wind is pushing you east, then you know that the airplane's going to really kind of, if it doesn't compensate for the wind, it's going to go this direction. And this is kind of logical, I think, for most of us. If we're going to head this way, but the wind's pushing us, our end result is going to look like this. We'll talk more about diagramming vectors and adding them on a grid on Monday. But what's really kind of cool about adding 2 vectors, when whichever format you're going to have them in, component form, if we know that vector A is 2I minus j, and vector B is 3I plus 4j, and we want to find vector A plus B, we are just going to take our corresponding components and add them together. So it's like 2I and 3I, and then if you actually even write it like an equation, and then combine like terms, 3I and 2I is 5I, minus j plus 4j is plus 3j, then we get that. Okay, so we will continue vectors on Monday. Feel free. You might be able to get up to problem number 41 on your homework, which is like half of day 1. We'll continue more on Monday and finish it up. Feel free to look at the examples in the textbook. Yeah.
Are the I's and J's just to distinguish between?
So I is always a unit vector in the positive x direction. So this right here, if I was going to draw it, I would go 5 units over in the positive x, and 3 units up, 1, 2, 3. So this vector would be A plus B. Does that answer your question? I is always...
What happened if it was going the other way?
So if it we can say, how far over do you wanna go? I
Like
don't care.
if it was a negative, I
-5, and what do you wanna do?
-3.
-3 down. So I would be going this way and this way. Here would be my vector. And I would write it as -5i -3j.
So the main reason we have the i's and j's is just so that we don't get an equation with 5 minus 3 and put them together.
Probably. We can also express this in the angle bracket format. Both of these are interchangeable. Most of the time your problem is just going to stick to one format, but this indicates the same exact thing as that. Just two different ways. Why are there two different ways? Not 100% sure. Vectors isn't my necessarily, area of expertise. I kind of have, base knowledge about vectors as opposed to someone in the physics department might have a better explanation as to why we have to do different formats.